So the second framework, which is actually a very interesting thing, unfortunately is not adopted very widely, is called the hierarchy of abstract machines, or HAM. Okay. Yeah, in fact, HAMs have become more like a curiosity in the RL community, as far as I at least I do not see anybody write papers about HAMs or anything. You talk to people who are working in the RL literature, right, they would have read upon HAMs at some point, but never given it very serious consideration after that. So Andy Bartow thinks that the HAM framework is the most elegant and most complete of all the three major hierarchical RL frameworks that are out there. Unfortunately, people just have not built a significant structure over it, except for people who work with Stuart Russell, right. So it was proposed by this guy Ron Parr, right. So yeah, the options framework was proposed by Doina Prikup, Rich Sutton, and Satinder Singh. So the original options paper was Sutton, Prikup, Singh is the citation for that, and yeah, it was largely largely Doina's work. Yeah. So I mean, when I start talking about options, other things I become a little nostalgic, because that's right about the time I was starting my PhD as well. So I have seen like 100 versions of options before it finally came into this form, right. So they talked about alpha models, beta models, and then beta time models, and they have a whole bunch of different versions of options before it kind of crystallized into this, right. And this whole connection of all of these frameworks, options framework, HAM and MaxQ, and all of these frameworks, the connections to SMDP Q learning were actually originally observed by Andy Bartow. So somebody was giving a presentation in one of the meetings, and then Andy just said, oh, that's SMDPs, right, and then people went and clambered around, and then they actually figured, oh yeah, okay, he's right. I mean, we are just, in some sense, many of the results that they were showing at that point were reinventing the wheel that people had done with SMDPs. So anyway, so going back to HAMs, I believe the HAM framework was the first hierarchical RL framework that came out, I think in 96 or something, 97 I think. But the options framework became more popular later, and mostly the work, all the follow-up work have been done in Stuart Russell's lab, and even Ron Parr did not continue too much work on HAMs after that, but it is a really cool thing, right, and it is also very complex. So what do I do with HAMs is that I am going to define, so what I call are simple machines that encode the policies that I am trying to follow, right. Machines, finite state machines, they are like finite state machines. I am going to define a hierarchy of finite state machines, okay, that is what we call now hierarchy. The hierarchy and the machines part is all clear, the abstract part will become clear in a minute, okay. So I am going to define a hierarchy of finite state machines, right. So the finite state machines will have the following types of states, 4 types of states, okay. So the first state will be what is called an action state, right. The second is called a call state, okay. Third is called a choice, fourth is stop, okay. So what does the action state do? It takes an input, emits an action, okay. What does the call state do? Takes an input, calls another machine, right. What does the choice state do? That's so confusing thing, right? Huh? Was that? Exactly. The choice state, well, I mean choice, it has to be a decision, right. So what do you do with that? What do you mean by decision state? Think of it in terms of finite state machines. What could it be? how will you encode decision making in a finite state machine? Huh? Close, you give a non-deterministic transition, right? Right. So essentially, a choice state makes a non-deterministic transition to two or more states in the same machine. Okay. So a call state calls another machine, but a choice state transitions to one or more states non-deterministically in the same machine. Right. And what does the stop state do? You think stops and then returns control back to the machine that called it. Right. So because machine would be called by a call state, okay, and there is also this starting machine, right, which is where you start your policy. Okay. Make sense? What is the input that you are going to see for these machines? States, right, the underlying states of the MDP. So the inputs to the machines are the underlying states of the MDP, right, and the outputs from these machines are come on, what do action states do? Yeah, that's the output, primitive actions. Primitive actions, it is going to take act states as input, primitive states as input, and it is going to output primitive actions, right. So the only output happens in the action state. So the call state does not output anything. What does the call state do? It just transfers control to another machine. So you keep going to one machine to another machine until you hit a action state. When you hit an action state, you emit an action, and that is when you actually move in the real world. Okay, make sense? Right. So this is how things will work. So I have this hierarchy, right? I have these machines. How does the hierarchy get established here? The calls, right? So the calls will give me a hierarchy. I have to make sure it is a proper hierarchy. I shouldn't have loops, right? If I have loops, then I can just keep calling around in the loop, and I can get into infinite depth into my policy. So make sure it is a proper call graph, right? So it should be a DAG, right? So make sure my machines are connected in a DAG, right? And then I start in the original machine. I look at what the initial state is. Right? That's the top level machine. Let's call it some M naught. So M naught will take a state, right, and then the start state in M naught will now make a transition. It could be the start state, could be a choice state, it could be an action state, could be a call state, whatever. It sees the input, and based on the input it makes a call, right. So it could start off one machine or the other, and then that machine now makes another call, okay, and finally at some level in some machine I am going to get a primitive action. Okay, if you think this is very complex, just think about how we talked about the getting out of the going to central station example, right. There is this one big machine that is going to central station, okay, it takes as input, okay, you are in the ICSR building, right, then it is going to say, okay, let me call the get out of inst machine. So I will go to the get out of inst machine. Get out of inst machine is going to look at the state, you are in the ICSR building, okay, go to GC machine. Then the go to GC machine will look at the state and will say, you are in the ICSR building, okay, and then it will call get out of ICSR building, and that will go down, it will call the get out of the classroom machine, right, and the get out of the classroom machine will say, oh finally, okay, move right, okay, that will be the first primitive action you do, right. So all of this processing happens, and then you move right, and then what happens? I am still in the get out of classroom machine because that is not reached a stop state, right. I keep moving until I reach the goal. I just do not want to exit and walk out to demonstrate the point, but you see what I mean, right. As soon as I reach the door, I will actually get to do a stop state in the get out of classroom machine. It will pop up and go to the get to
previous machine, which one, which called it?
Yeah, memory is so low, is it? What machine called it? Get out of the ICSR building, right? So that is the machine that called this. It will go to the get out of ICSR building. Now what it will do? It will say, okay, you are no longer in the classroom, right? So it will see that. Then it will say, okay, go down the stairs machine, right? And the go down the stairs machine will then allow me to take my actions one after the other. So it will give me a series of primitive actions. I will walk down the stairs, and then it will reach a stop state, and then it will pop back up to the get out of building machine, and then it will finally say okay, walk out of the door machine, then it will go back and call that machine, it will go back up, and now I will make a transition in the get out of, go to the GC, it will go back up, I am already out of the building, so it will go back one more level up and it will say great, now I can go to the GC, right, it will call the go to GC machine and then go off. Okay. Given analogy?
Take a lift or stairs.
There you go. If the lift working, right, if the lift is working, then I will go to an action that says take the lift. If the lift is not working, I will go to the action that says step down. That is a choice state. No, I am defining go to the lift as a primitive action, and it could be a choice state. I mean, it could be a call state. The choice state can make a transition to a call state. I did not say it has to make a transition to the primitive state. So the choice state, I will actually draw a simple. So this is easier to connect to, right? Whatever I described, you can understand how HAMs are going to be used and so. But there is also an example from the paper. So how many of you looked at the recent advances in hierarchical RL paper? That has already been on, it's on Moodle since the last class. Read the first 4 sections, you do not even have to read the 5th section, okay. So anyway, yeah, so going back, let's take another example that they have here. So the problem was to do some kind of a very complex so they had a very complex grid world task, okay. Each of these corridors will be divided, so there will be like 10 grid cells here, right. This is a pretty large grid world, right. So some 300 by 400 grids or something like that, and all along the corridor, okay, there were small obstacles, right. They in a specific shape, there is like this shape, like this, right. They have put obstacles all around the corridor. So whenever you are going around, right, so you might hit an obstacle, and you are supposed to find your way around the obstacle. You are trying to learn your way around the obstacle. So what you can either say that you are going to follow the wall, you know. So if I hit the obstacle here, I can essentially follow the wall and I will get out, right, or I can back up, go back the way I came, turn in arbitrary direction and walk to see if I will evade the obstacle. Okay, these are 2 ways which you can get around the obstacle, and so they wanted to come up with a machine that learns how to do this, right. So what they did was they defined it as follows. So they have a follow wall. Why doesn't?
Q-learning can find the same trajectory. Q-learning or SARSA here.
Yeah, sure.
It will be very bad.
Huh? No, you have a lot of time, sure.
300 cross 400.
Huh?
300
cross 400. A lot of it is repeated, right? I mean, once you know how to avoid one of those bracket shaped obstacles, then why do you have to relearn everything again and again, right? There's a whole idea of going to hierarchies that you don't want to keep learning the same thing again and again. Right, so I'm going to follow the wall, right? Start somewhere, I'll just keep following the wall. Then what I do, right? So if I hit an intersection, so this is a call state, okay? So I am calling the machine for following the wall. So there might be some things that I need to do, because assume it's actually a robot, I might need to position myself a distance away from the wall and then keep moving and things like that. So when the follow wall command, the machine returns, I will be in some state, right. So I could be either in an intersection, I am assuming that as long as I can validly follow the wall, this machine will run, right. When it comes back to this machine, right, when the follow wall machine terminates and comes back to this machine, I will either be at an intersection or I will be at a obstacle. At an intersection I stop, basically I go back up, because when I come to an intersection, right, now I have to make a choice of whether I have to go this way, that way, or this way, right. So that choice will be determined by a different machine. Okay, so my job here was to walk from this point to this point, that is the goal of this machine. You can think of this as navigator corridor. Okay, this machine is essentially navigating corridors, right. So if you start it off here, it will go all the way here, it will stop here and it will tell me okay I am done. But if you start it off here, maybe it will go here or here, one of those two things. You give it a proper direction, you say go in this direction, it will go all the way here, it will stop and then it will come back. Okay, so that is the goal of this machine, it will navigate a corridor. Okay, so it will stop, follow wall will stop if it reaches an intersection, because there is no wall here, so it will stop. Okay, it will say okay I have reached the intersection, and then if I have reached the intersection I am happy, I will just stop and I will give it back. If I reach an obstacle, then what do? I have a choice. Okay. So what can I do? I can, two choices I have, I can pick a different wall and follow it, right, or I can back off. These are the two things I can do. So what is back off? Back off is another machine, like I was telling you, it moves me back in the direction I came. Okay. So this is, remember this is not a real machine, okay, I am just, this is a sample thing. Okay. So the choice state I can either say follow wall, okay, or I can say back off, or I can even say stop if you want, I mean I do not care, right. So the choice state allow me to go to any one of these three things. Okay. And what do I do with back off? So it is another machine I call, it will, when it returns I either reached another obstacle or I have reached an intersection. Okay, if I reach an intersection I stop, basically it could very well be that I went all the way back, so that I went back to where I started, right, or I reached another obstacle, so I came back and tried to do another choice state, pick a different wall and follow or whatever, right. So sorry,
what's the choice you make in the smart choice?
what is that?
Choice you make in the smart choice.
Choice I make it what?
The square that you make. What is the choice you make?
It just says choice. It is a non-deterministic transition. So in this case it can go to any one of the other three states in the machine. It could go to follow wall, it could go to back off, or it could go to stop. Or you can limit it, you can say no you can't stop, you can go to only one of the other two options. That I can say that okay you can either go here, okay, that is your non-deterministic transition. So from choice you can either go to follow wall or you can go to stop. Don't think of it as a realistic way of solving this problem, please. Okay, just a simple illustrative machine, it might not be the actual machine. Okay, great. So any questions on this? So let me at least try and finish this today, and then I can start max Q tomorrow. So give me a few more minutes. Follow? Oh, that's another machine, just like a hierarchy.
Call state is what?
Those are call states.
But those are action, right?
They are call states.
Where does action happen?
Action will happen somewhere down there, right? So follow wall might say, okay, rotate my motor.
Okay, it's there in between the follow wall and stop. It's action state.
No. Follow wall is another machine like this. Okay. So there will be a follow wall machine. Okay, that will come somewhere like this, right? So maybe not a choice state. I don't know. They don't have a symbol for action states. I don't know. There will be some action. It will say move right, right? There may be actions for moving right, moving left, or whatever. So you come here and then you decide whether to move right, move left, and so on and so forth. Right? So it will be another machine with action states in there. So this machine has no action states. Okay, all fine? Fine? Everybody fine on board? Huh?
Call state here.
What's that?
Which are the call states here?
The call states or follow wall and back off. Okay, so in this we have call states, choice states, stop states, no action states. The action states will come further down somewhere, which will be things like actions like move left, move right, or turn motor. So much depending on whatever is your primitive action. Okay, so that will come in some other machine. We are not looking about that. Here is my question to you: where is RL here? What do you learn here? Where is the SMDP here? I am talking about a different hierarchical framework. It is no longer options here. You should forget options while I am talking about HAMS. There are primitive actions, but where is my SMDP here?
Call state. Call state.
So what do you think I should be learning?
Which call state?
Huh?
Which
Which machine to call? Or essentially, what do I do in the choice state, right? Choice state need not be machines. It could be other action states also. Right? It could be I could come to a choice state and then say, okay, if I am here, then go left. If I am here, go right. I mean, I can look at the actual the what they call it, the core MDP state, the base MDP state. Basically, that's the input I am getting, right? I can look at the input in the choice state. I can say go left, go right. I mean, it could be primitive actions also. I could be transitioning to action states. So I have multiple choices that I could do in the choice state. I really have to learn what is this choice I should make, right? But where is the SMDP that I am going to learn on? Huh? Where is the SMDP? Give me a specification of the SMDP. So what are the states of the SMDP? So if you remember in the options case, the states of the SMDP were the same as the original states, right? And the actions of the SMDP were essentially the actions plus options. I told you, right? You might have 4 actions and 6 options. Totally the SMDP will have 10 actions, right? So likewise, where is the SMDP in this case? What is the state space? Huh? The call states and the choice states. No, the underlying MDP is, we can throw it away, is it? That doesn't form part of the SMDP. So I need to have my base MDP states in my SMDP because I have to learn a policy that is a function of where I am in the world. Right? I cannot ignore the base MDP state, right, or the core MDP state. I need the core MDP state. But what action I pick also depends on what machine I am in. Right? It not only depends on what machine I am in, it also depends on who called it, right? Once you are outside the building here, depending on whether you are going to the main gate or Velachery gate, depending on which machine higher up call the get out of building machine, I might have to take a different action. It does not just depend on whether I am in the get out of building machine, it also depends on which machine called me, right. In fact, there is a stack. I have to keep a stack. I have to keep a call stack. Which machine called which machine, which machine called which machine. So that call stack has to be part of the state space, because what decision I make depends on the entire call stack. So now what are the things that need to be part of the state space? The state of the base MDP and the call stack, right. Great. So now what are my actions for my SMDP?
What's the point of it being the actions being dependent on the machine which called this machine?
What is my action space here? Is this the actions of the core MDP?
And also taken the transfer from one.
Huh?
Transfer of.
You're getting more context to take an action. Right?
What's that?
You're getting context to take an action.
I have states and I have the call stack.
Yeah. So call stack provides more context than just the.
No. First answer my second question. That's the reason I didn't answer his question. I can't answer his question until you answer my question. What are the actions here?
Primitive actions
Pause,
plus.
make choice.
I will tell you, the primitive actions are not the actions that I am going to look at in this SMDP. I will ignore the primitive actions in the SMDP because the primitive actions are all already predetermined. If I land in an action state, I will emit a primitive action, right. I have no choice over that. I am giving you hints. So what should be the actions? Transitions possible out of the choice state. Therefore, two of those actions would be follow wall and back off. there will be 2 of those actions that will go into my SMDP, right. And once I call follow wall, it is like an option I have called now, it will keep running until it reaches a intersection, maybe there might be other choice states within the follow wall option, in which case it will come back to me and I will have to make a decision what to do with that. Okay. So essentially the SMDP consists of I don't know, I am going to call this as HI is the call stack, right. It is a history of the things I have called, it is essentially the call stack, right, and SI which is the core MDP state, right. These are the this cross this, right. So this will be my action space, okay, that will be the call stack times the current state, right, that will be my state space, right, and my action space would be all the outcomes of the choice state Ci, right. So all the possible outcomes of the choice state Ci will be the actions I can take, right, and of course there will be some limitations. I can take a particular action only if I am in a choice state corresponding to that machine, right. So I need to know which choice state I am in. So I not only need the call stack, what else do I need?
Why can't it be a provision?
I need to know what state, machine state I am in as well.
So like in the call state,
Yeah.
in the call state, you move to some other machine, right? Even you make a that could be a part of the
No. Yeah, choice is the call state could be an action state, provided it is something which I can reach to from a choice state. If I have a machine that is completely specified without any choice state, none of the states in the machine will appear in my actions, right. I could define a machine without a choice state, I mean I could know the policy completely beforehand, I do not have any learning to do for a particular policy. For example, we have been talking about options, right. So if I am trying to encode the policy of an option, it will be a machine without a choice state. Suppose I have defined an option, get out of this room, right. The machine for corresponding to that will look like, okay, sense the world, right. So okay, there is a, if you are in this state, then back off, right, until you reach here and then turn right, and then walk out, right. So it will be essentially there will be no choice states here, this entire machine will have no choice states, right. It is possible, and none of these things will actually appear in the none of the states that I have in this machine will appear in the actions for the SMDP. No, the choice could depend on the call stack, right. Why? Depending on where you are, you can choose to go left or right, depending on your call stack.
Depend on what your overall goal is.
Could that's a, it gives you the freedom for defining it that way. I am not talking about learning recursive optimal policies here. I could learn hierarchical optimal policies when I am using HAMS. So it's actually pretty powerful framework. It allows you to do all kinds of things. In the options thing, that question doesn't even arise because I have frozen my hierarchy, right. We are talking about this in the last class also. It kind of becomes degenerate, right. So recursively optimal is equal to hierarchically optimal in the options case, because I can't change the policies. We have to assume whatever policy is given to us is optimal. But here I can actually, if I start conditioning it on the call stack, and I can potentially think of learning hierarchical optimal policies. Okay. Is it fine? So I need the machine state also. I need to know which choice state I am in. There could be multiple choice states in a machine, right. I need to know which choice state I am in also. Right? And so I take all of this together, and then my actions are essentially other machine states, I don't know what to call it, right. So SM or machine states, so actions are these machine states, it could be one of these states that I have to go to, right. So this is essentially my SMDP, and the transition function are defined by, okay, if I choose to go from here, the action I take is follow wall, then that machine will call, it will keep running till the end of that machine's execution, and then it will come back here, okay. So that is essentially the transitions, yeah.
What is machine state here?
Machine states are these finite state machine states, one of these machine states. which state I am here, right, when I actually come here, which is the state I am in when I make the call.
Won't that be just the top of the call state?
No, that is the machine I am in.
Okay.
This will be the machine state I am in.
Oh, okay.
So which is the path through the tree would be there, the DAG would be there, and this will be where in this machine I am. Okay. So I mean I might be kind of fudging the notation a little bit. You can read the paper and find out what the exact notation is, but so that's I am just trying to give you the intuition. I am not trying to lock down everything. So there's one other thing which I wanted to tell you. And how would now that you know what are the states, right, and what are the actions, right, you can learn policies using SMDP Q learning, right. So what is the weird thing about this? This is another thing which I wanted to mention. So whenever I make a call action, right, or a choice action, right, whenever I go to a call or a choice state, there is no transition in my core MDP state, right, only the machine state and the call stack could change. So the only time my core MDP state changes is if I visit the action state anywhere in any of the machines, right? I do not care, right, whenever I am in the process of executing the policy, if I reach an action state, then the core MDP state will change, otherwise that component will stay the same, right, and only these components will change. Okay. So this is essentially the idea, right, and so the thing about this is, so what will be the equivalent of an option in this case? So the option encapsulates an already learnt policy, right. So what is the equivalence of an already learnt policy here? Without any choices. What without any choice states? Any sequence of action states you visit without any choice state in between, right, I mean those would constitute your policy or an execution of the policy, right. So because when you are running this machine, if there is a sequence of states that you visit, sequence of action states you visit without a choice state in between, right, that will constitute a learnt policy. Make sense? Because that is already pre-packaged, right, I have no choice there, that is like an option. Once I pick the option, I just have to take the action suggested by the option, so like that. So that is the thing. So as you can see, this is a little more complex than the options framework, right. So people are not very, did not take to it too kindly, but if you think about it, it's a very powerful framework. It allows you to do recursive hierarchical optimality, it allows you to work in partially observable states, right. So when you do not need to know the full state spaces, because one of the nice things is you can use this kind of finite state machines to define more complex policies, right. You can define non-Markov policies easily, you can have finite state machines with memory, right, you can define non-Markov policies. So the representation itself is very powerful, but unfortunately it just gets very complex, so people are not very fond of this. Okay, I will stop here, I will continue with the max Q thing, and also more discussions on hierarchy, specific abstractions and other things in the next class.